But we're going to use this CO2 in the atmosphere as an example to look at chemical reactions. So we've talked about chemical changes, and chemical reactions are chemical changes, or description of a chemical change. We have one or more substances that are destroyed and converted into one or more new substances. Chemical reactions always involve the rearrangement and exchange of atoms. The atoms themselves are unchanged. There are nuclear reactions where atoms are changed, but that's not what we're talking about here. So again, I like to think of atoms as being Lego blocks. And so your chemical reaction, you're starting with some Lego blocks, and you're taking them apart and putting them back together in a different way to make new things. The Lego bricks remain unchanged. It's just how they're associated with each other. So a combustion reaction is a particular type of reaction in which a substance combines with oxygen. And in this process, it forms one or more oxygen-containing compounds. So combustion is burning. Oxygen is required for something to burn. So the heat that's produced by combustion is very important in supplying energy to our society, right? So the combustion of gasoline in a car causes the car to move forward due to the energy that's released. We can burn coal or other fossil fuels to generate electricity, etc. So in a chemical equation, we have a shorthand way of representing a chemical reaction. And the general idea here is that we have the reactants on the left and an arrow pointing to the right and the products on the right. So we read left to right, we read the equation left to right, we start with the reactants, we end up with the products. The reactants react to produce the products, right? And there's a lot of information in the chemical equation. It gives us the formulas of the reactants and products. It often gives us the physical states of reactants and products, and these are the symbols that we use. These are called state symbols, and they're put in parentheses after a chemical formula. So G for gas, L for liquid, S for solid, and AQ meaning aqueous is dissolved in water. We can also get the relative numbers of reactant and product molecules that are involved in the chemical reaction, and we can use chemical equations to predict, well, if I burn this much fuel, how much energy am I going to get? How much CO2 is going to be released? So those sorts of calculations are the focus of this chapter. So let's look at the combustion of methane. So methane is CH4, and anytime we have something burning or combusting, we have combination with oxygen. Oxygen is a diatomic element. At room temperature, it's in the gas state, and so it's listed here as O2 with a G after it. Here, oxygen is alone, and so it's important to write it as O2. Over here, oxygen is with hydrogen, and so I told you I think of these elements as being like junior high girls, so they don't go anywhere alone. So here, when it's just oxygen, junior high girls, they're going to go out in pairs. But over here, this oxygen is with two hydrogens, and so she's totally fine with being the only oxygen there with the two hydrogens. So the O2 is when the element is by itself. I know that can get confusing sometimes. So when methane burns, it produces carbon dioxide and water. So the carbon from the methane turns into carbon dioxide, and the hydrogen turns into water. And these are the products that would be collected in one of the combustion analysis instruments where you collect the hydrogen and carbon emitted and figure out the empirical formula. So if we look closely at this formula, this equation, CH4 is 1 carbon and 4 oxygens. Here we have 2 oxygen atoms. Over here in CO2 there are 2 oxygen atoms, and in the water there's 1 oxygen atom. So we're starting with 2 oxygen atoms and we're ending up with 3 oxygen atoms. So as it's written, this indicates that we're pulling a Lego brick out of nowhere. right? One that we didn't have to start with and now it's there. And that's not possible. So it doesn't mean that the law of conservation of mass is wrong. It means that our equation needs fixing. We also have a problem with the hydrogens. Over here on the left, we've got 4 hydrogen atoms, and on the right, there are 2 hydrogen atoms. Seems to suggest that 2 hydrogens went bye-bye. Maybe they turned into the missing oxygen. No, that can't happen in a chemical reaction. So this equation is not correct. It's violating the law of conservation of mass. So we need to fix it. We balance the chemical reaction. When we balance a reaction, we change coefficients. Those would be the numbers in front of the formulas. So we can say, well, there are 2 oxygen molecules. We can't change, bless you, we can't change the formula for oxygen. Oxygen is always O2. But we can say, well, what if there were 2 molecules instead of just 1? So here we've got the chemical equation, and then we also have pictures representing the molecules. So now with 1 methane and 2 oxygens, we can take these guys all apart and put them back together like this, and we're going to get 1 CO2 and 2 water molecules. Okay? Look at that and see how that's working. Because this is the visual picture. This is what we need to be able to see just in our minds when we look at chemical equations. This is what's happening. So you can imagine taking this apart. There are 4 white balls, and those 4 white balls end up over here. There are 4 red balls, and we've got 4 red balls over here. There's 1 black one and 1 black one. All the Legos are accounted for. This is a balanced chemical equation. So we're going to look here at this chemical equation and count the atoms. So how many oxygen atoms on the right-hand side of this equation? So we're looking over here, and there are oxygens in both of these compounds. So in this part right here, oops, I guess that could work. How many oxygens are indicated there? 6. There are 2 of these formula units, and each of them has 3. So there we've got 2 times 3 is 6 oxygen atoms right there. And then over here, how many oxygen atoms? 8. 4 times 2. Each CO2 molecule has 2 oxygen atoms, and there are 4 of them, right? So a total of 8. And so over on the right side, we have 6 plus 8 is 14 oxygen atoms. Any questions about that? Does that match up with how many oxygen atoms are on the left side? Here we've got 2, and in here we've got 4 times 3 is 12. 12 plus 2 equals 14, right? So any questions about that? So we need to learn how to balance chemical equations. And again, this is something that you've done before, but it might not be there real solidly. And so we're going to go over it, and we're going to get better at it. You start out by writing a skeletal equation. So you need the formulas for the reactants and the formulas for the products. And it's important that they are correct formulas. Because if you've got the incorrect formula, your equation's going to be wrong, and it may be impossible to balance. The rest of this is sort of guidelines. There is no one set of steps, do this, 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 and this, and you'll end up with a balanced chemical equation. This is called balancing by inspection, meaning you'll look at it. Okay, but there are some guidelines. So in general, if you look at the atoms that occur in the more complex substances first, work on those first, and then anything that occurs as a free element, leave that one for last. That's generally a good idea. If you balance it and you end up with fractional coefficients, we need to clear those out. because a balanced chemical equation has the lowest whole number coefficients. And then always check your work at the end. So we're going to do some examples here. We're going to get a little practice with nomenclature in, so hopefully this will help keep that part of your brain active for the exam. So write a balanced chemical equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So we need the formulas for the reactants and products first. This sentence is describing the chemical reaction. So we've got solid silicon dioxide and, that's the plus. Actually, let's do it this way. No, that's too fat. Adjust that. And is plus. To produce, that's the arrow. And this and is another plus. So I need the formula for silicon dioxide. What kind of a compound is that? It's molecular. So we find silicon on the periodic table, and it's on the non-metal side of the line. Now it is a semi-metal, but it's on the non-metal side, and so it's going to be named as a molecular compound. So silicon dioxide, we're using the prefixes. So there's no prefix in front of silicon, and so that's just one silicon. I didn't mean for that to be, I wanted that to be blue. Silicon. And how many oxygens? 2. So SiO2. And then we're told that it's a solid. So we can put in parentheses S to indicate the solid. Sometimes state symbols are very important, other times they're not. But since we can do them here, we're going to practice. And then we have a plus. And then we need the formula for solid carbon. Well, carbon is C, and it's a solid, they tell us that. That's an element. Is it one of the 7 diatomic elements? No, it's not. So it's just C. Okay? And I'm leaving a space here because I might need to put a coefficient in front of it, and that makes things less messy later. Arrow. Silicon carbide. Well, silicon is a nonmetal, and carbon's a nonmetal, so this is a molecular compound. SiC. Now, it doesn't say silicon monocarbide, but it doesn't say something else, and so we're just going to go with that. Hey Siri, what's the formula for silicon carbide?
The answer I found is CSI.
Interesting. So it's like every semester she changes. So now she's telling me it's CSI. What was really fun is about a year ago, I asked her that, and she'd say the formula is sick. She'd actually say it out loud. I keep hoping that she'll go back to that, but not so much. Okay, silicon carbide, and that's solid. Plus, leaving a space for a coefficient, carbon monoxide gas. What's the formula? CO gas. Monoxide means 1 oxygen, right? Okay, so there's the skeleton. Now we need to see, do we have the same number of elements on each side? So here carbon is by itself, and so I'm going to leave that for the end, because I can put a coefficient in front of this one, and it's not going to mess up anything else. Generally, if you just start with the first element and work your way through, things go pretty well. If you find that you're going in circles, like you keep changing the same coefficients and you don't seem to be getting anywhere, double check that your formulas are correct. And if the formulas are correct, just start over in a different place. Okay, so I'm just going to start with silicon. How many silicon atoms are on the left side? Just one. And how many are on the right side? One. Well, that's nice. Off to a good start there. How many oxygen atoms are here? 2, and there's not any here. So I've got 2 on the left side, and over here I have only 1. So to make it 2, I put a coefficient in front of the formula. Say there's 2 of these molecules. I can't change the molecule to CO2 because that would be different. Okay, so we've got the silicon and the oxygen taken care of, and now we can look at the carbon. So on this side I have 1 carbon, and over here how many carbons? 3. So what do I do over here? Put a coefficient of 3 in front of it. Okay. There, in general, are different ways that you can approach and come to the balanced equation, but we should all come to the same balanced chemical equation. Any questions? Let's do another one. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. Very gassy problem. So we have ethane combining with, so it's plus, to form is the arrow, and is the plus sign. So we're translating a sentence of words into a chemical equation. So our first reactant there, gaseous ethane, they gave us the formula, C2H6, and they tell us it's a gas, so I'm going to put G. And what is that combining with? Gaseous oxygen. So what's the formula for that? O2, because oxygen is one of the diatomic elements. So this is an example of where we need to remember which ones are diatomic. So there's the gas, and that's going to form carbon dioxide. What's the formula for that? CO2, carbon dioxide, 2 oxygens, also a gas, and water. What's the formula for water? How do you know that? Because you memorize it, right? It is. Water is H2O. And here it says it's a gas. Sometimes you have to predict the state symbols. If you have no other information, you would assume that it's occurring at room temperature. Here, this is natural gas burning. Is this going to be at room temperature? No, it's going to be hot, right? So at an elevated temperature, the water is going to be in the gas form. Okay, so let's balance this one. So I'm going to show you, it's sort of an inventory method that some students like. Oops, did not mean to do that. So we're going to take inventory because this one can be a little messy. There's oxygens and hydrogens all over the place, and carbons, and it's just kind of a mess. So one way to do this is to just draw a big vertical line at the arrow so you can clearly see the 2 sides that we're trying to balance. And then I'm going to list the elements and just take inventory before I start adding coefficients. So there's carbon, there's hydrogen, there's oxygen. Those are the only 3 elements. So here on the carbon row, I'm going to write how many carbon atoms are in that. There's 2. And in the oxygen, there aren't any, so I'm just going to leave that blank. And over here in CO2, how many carbon atoms? 1. And in H2O? None. So hydrogen, in this first compound, how many? 6. And in O2? None. CO2? No hydrogens. And over here on water, 2 hydrogens. And the oxygens, in the first one, there's no oxygens. Whoops. I was thinking O for oxygen. In O2, there were how many? 2. In CO2, there's 2. And in H2O, 1. So now we can look a little more clearly to see, are these things balanced? So here, the total for carbon is 2 and 1. That's not good. For hydrogen, it's 6 and 2. That's not good. For the oxygen, it's 2 and 3. Nothing is balanced. Great, right? So let's just start with the carbon. So I've got 2 carbons on this side, and I've got 1 on the other side. So how can I fix that? I can put a coefficient of 2 in front of the formula. So I put a 2 here. That changes how many carbons and how many oxygens there are. So I'm going to adjust that. Now I have 2 carbons and how many oxygens? 4. 2 times 2 is 4. Okay? So my carbons are balanced. Did you have a question?
Oh, just in the one. It's like H2O plus the oxygen. So there's 5.
Yeah, but I'm not looking at oxygen right now. There are 5 oxygens. I'm starting with the carbons. And yeah, so we're just going to work our way down. Okay, so carbon's okay. Hydrogens, I have 6 on the left and 2 on the right. So how do I make a 2 into a 6? I multiply by 3. So I'll put a 3 in front of H2O, and then that's going to multiply all the numbers underneath, right? Now I've got 6 hydrogens and 3 oxygens. Did that change the carbons? No, it didn't. So that's okay. So carbon and hydrogen are balanced now, and now we go to oxygen. And oxygen is good to leave for the last because it's present as an element. So I've got 4 plus 3 is 7 oxygens here, and on the left side I have 2. How do I make 2 into 7? Well, you can't do it multiplying by a whole number, right? Because it's an even number, and how do you make an odd number, right? So there's 2 ways to fix this. You can do a fractional coefficient. If you multiply that O2 by 7 halves, that'll give you 7 oxygens. Most students don't like fractions, so I'm not going to do that one. This is what I call an odd-even problem, where I've got an odd number on one side and an even number on the other side, and things don't look very good. I can make an odd number into an even number by multiplying by 2. So I'm going to multiply by 2. So I can multiply this by 2. That'll give me 6. And I'm going to multiply this one by 2 also. And that gives me 4. So down here I've got 12 and 6. And this is 4 and 8. And now I've got 14. An even number. To maintain the balance of the carbon and the hydrogen, I'm going to multiply the other side by 2 also. So I'm going to change this to a 2. This becomes 4 and 12. Yeah. I didn't put a 2 in front of the oxygen because this is the one I'm trying to fix up. But I doubled everything else. And so the carbons are still balanced. There's just twice as many. The hydrogens are still balanced. There's just twice as many. And now I need 14 oxygens over here, and they're coming in pairs. And so I can multiply this by 7 and get 14 oxygens. Any questions? Some equations are easy to balance, and some of them are a real pain in the butt. So the combustions of hydrocarbons can get messy, and that's why I showed you this inventory method for this one. Yeah?
So we multiply by 2, we just multiply the reactants, or did we go back to...
I multiplied everything except the oxygen that I was trying to fix.
Right.
So I had adjusted carbon and hydrogen, and so anything that I had adjusted previously I multiplied by 2. And this is the one I had left to make it balance. So I didn't multiply that by 2. I could have,
Oh, okay.
but yeah, it's,
The whole point was to do it.
the whole point was to get an even number over here
Right.
because the oxygens are coming in pairs.
Okay.
Yeah. Sometimes you balance an equation and you end up with coefficients that are not in the lowest whole number ratio, and then you have to simplify. It doesn't happen often, but it could happen. Anybody else have any questions about this one? That's an excellent question. So if you balanced using 7/2, is that wrong? It depends on how picky the person who's reading it is. Master in chemistry will say it's wrong. Technically, it's balanced. You could use that to do stoichiometry or successfully calculate other things, but if you're asked to give a balanced chemical equation, they need to be whole numbers. So we should always clear fractions if we get them. Anybody else? Let's do another one. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. So again, the ands are the plus signs, and to form is the arrow. Now these are ionic compounds, right, because they've got metals in them. We've got lead and potassium. Those are both metals. So writing the formulas for these chemicals, these compounds, requires that we look at the charges on the ions. And so we need to make some notes off to the side. So for aqueous lead-2 nitrate, what's the formula for lead-2 ion? It's Pb.
Plus 2 charge.
Yeah, with a plus 2 charge.
Nitrate, NO3.
Yep, NO3, nitrate, NO3 minus, because we memorize it. Right? So this is 2 plus because the Roman numeral tells me it's 2 plus. The Roman numeral is the charge on the ion. It is not the subscript. So I look at the two of these things and their relative charges to figure out how many of each do I need so that I get a neutral compound. There's different ways of looking at it, but I'm going to need 2 nitrates so that I can have a total of -2 charge and +2 charge, and that'll be neutral. So this is going to be Pb. I have 2 nitrates. Those are polyatomic ions. So I need to put shrink wrap around them and the number of them on the outside. It's like a bundle pack at Costco, and it's wrapped in shrink wrap, and the number outside says how many of the things in there do you have. I'm told it's aqueous, so then I put AQ. Okay, what's the symbol for potassium ion? And the charge? +1. Why? It's in group 1. Okay, group 1 metals, +1 charge. And chloride is from chlorine, Cl -1. And the periodic tables start with the noble gases and count backwards. So we're just counting one column backwards, -1. So here the charges are opposite and equal, and so we just need one of each, KCl, aqueous. On the product side, I have lead-2 and chloride. So lead-2 is still Pb2 plus, and chloride is still Cl minus. So I need 2 chlorides. This is not a polyatomic ion, it's just an atom with a charge. And so when I need 2 of them, I can just put a 2 here. It's not going to be confusing because it's not a polyatomic ion. That's aqueous. And then the last one is potassium nitrate, potassium ion, nitrate ion, +1 and -1. And so KNO3, aqueous. Yes?
Isn't the CO2 supposed to be a solid?
Yes, thank you. Got a little carried away there. Solid lead 2 chloride, and I put AQ. Thanks for catching that. Any other questions? So that's the start. And then we have to balance it. Well, this is a, as the title says, balancing chemical equations containing ionic compounds with polyatomic ions. So we have this polyatomic ion, nitrate, and it's present in the reactants and it's present in the products. And this happens a lot. The nitrate ion acts as a unit and it doesn't get taken apart. So we can balance nitrate as a unit instead of looking at nitrogen and oxygen separately. You can do the elements separately, that's going to work also. Usually people find it's faster to look at it as a unit. So here I have nitrate and there I have nitrate. Here I've got how many nitrate ions? 2, and over here I have only 1. So how can I make there be 2 nitrate ions? I'm going to put a coefficient in front and I say I have 2 of those formula units. I can't change the subscripts because that changes the compound. So that was nitrate. What about the PB? How many PBs do I have on the left side? 1, and over here, 1. So that's good. How about K? Potassium. There's 1 here. And how many over here? 2. So how can I fix that? We put a 2 in front of KCl. So I've got 2 potassiums. And then the last one I haven't checked yet is chloride. So 2 chlorides, and over here, 2 chlorides. Usually that last one will kind of take care of itself. So there it is. This is something that requires practice, like riding a bicycle or something. You know, you just have to get out there and do it. You fall down, you skin your nose or something, and you get back up and you do it again. The good news is there will be no blood involved in learning how to do this, right?